large man, and he got in the bath, and water splashed out of the bath. And he jumped up in his birthday suit and said, and ran through the town, legend has it, yelling, "Eureka!" Right? And I don't believe, I think it's apocryphal, but he's a very dignified guy. I don't think he's done it. But let's pretend it's true. So what was he saying Eureka for? What did he discover? He jumped in the bath, the water was displaced, came out of the top, overflowed the bathtub. He said, oh, if I want to measure the volume of something, doesn't matter what shape it is, I can just submerge it and then measure, right, how high the water goes up as a result of this thing being submerged. And in fact, this is how you measure body mass index and things like that. It's essentially a density measurement. We know what the density of the body is. How you do it? It's easy to measure the mass, just on a scale, you measure your weight, you divide by G, and that's your mass, right? But if you want to know what the density is, you need to know what the volume is. So Archimedes figured out, very smart fellow, you put the object fully submerge it in a tank with using really, actually, you don't use any spread at all. You can leave it at the bottom of the tank, just put it down there. And it raises the water by some amount, and you measure the height, and you know what the area is, right? You know what the delta H is, and you multiply them, and that's the volume. And so you can figure out the density, right? Volume by density. So if you have two things that weigh the same, and you want to know if you have the same density or not, they better have the same volume. So that's what you can do. There's another way to think about it, though. So what I just described is how you explicitly measure the volume of the object, and then you calculate the density. Another question is, well, what happens if you've got your balance all set up like this, and these things balance, but now you submerge it in water. So now just dunk both these guys in water. What would happen? So suppose this thing has lead mixed in. There's some gold, and remember, lead is more massive than gold, right? So I'm right about that, aren't I? Yeah. Where is it? I can't even see lead up there. I see gold. Oh, there it is, just to the right a little bit. Yeah. Thank you. Yeah. It's 3 over to the right, right? It's PV, right? So it's a little bit more massive than gold. So what does that mean? It means that if these things have the same mass, which one is going to be smaller in volume, the crown or the block of gold? Crown's got some lead in it. This has only gold. They have the same mass. Which one's going to have the smaller volume? The thing that's got lead in it, the crown. The way to think about that, forget about the gold. Say, what if this were all lead and this is all gold, right? Because if you have 50-50 gold and lead or something, well, that's going to be in the direction that would be if it were all lead compared to being all gold. So this guy is going to have greater density or smaller density if it's got lead in it. Greater, because lead's more dense than gold. So that means that his volume, the crown's volume, will be bigger or smaller than the volume of the plain old gold at the same mass. Smaller. So if you submerge these guys, what happens? So if you submerge them both in water, right? Now what happens? They're not going to be balanced anymore, right? Because they have different volumes. They're experiencing different buoyant forces. Does that make sense? This one's smaller in size, smaller volume. So does it experience a bigger buoyant force or a smaller buoyant force than the other one? Smaller buoyant force, because the buoyant force, after all, it's a rho g times the volume of the submitted part of the object, right? Well, this is small, but it's fully submerged, but submitted. You can tell what I'm doing later. Submerged. That's what I meant to say. So the submerged volume is smaller because they're both fully submerged, so it's just a matter of volume, right? The volume of the crown is smaller than the volume of the block of gold. Therefore, this is smaller for the crown, and rho of the fluid is the same for both. The density of the water is the density of the water, right? So for this formula, the only thing that matters for the buoyant force, right, is the density of the fluid you're submerged in, and the volume submerged. The submerged volume is smaller for the crown, so you get a smaller upward force due to buoyancy. But the downward force due to gravity is the same for both objects. They're the same mass, right? We weighed them before we submerged in the water. So which one sinks, the crown or the gold? The crown, but it's smaller, has a smaller upward buoyant force compared to this buoyant force, but they have the same downward force of gravity. So the crown sinks, and the jeweler gets bad news, right? I think that's what happened, in fact. I think they did discover that they weren't, because nobody knew how to do that before Archimedes, right? I mean, the jeweler thought he had it made, the artisan, because how's the king going to check? There's no way he's going to ruin my beautiful finery on the outside of the crown. Actually, I should research that story myself. That's true. I think it's true that they found that the guy cheated him. But anyway, in any case, it's hard to know from antiquity. You know, all kinds of stories around. Like Eureka thing, I don't buy it. You know? But anyway, so that's good people think that's true. Here's a more sophisticated version of this, in fact. So what I'm going to do now, this pump will continue to function for me as it did nicely earlier. I'm going to take the air out of this cylinder. So what's going on? I've got a bell jar. It's got air inside right now, okay? And there's two objects hanging on a balance. You see that? Oh, no. Let me get down on the big screen, this bell jar right here. When that happens, what you'll see is a bell jar with a round thing on the left. Oh, there we go. Very good. Perfect. That round thing you see is a hollow. It's a brass sphere that's got air inside. The thing on the right side is a solid piece of brass. And they're equally balanced in air. So this is a more subtle test than the one we did with the crown. With the crown, the air, we didn't worry about buoyant forces due to the air. That was a pretty small effect. We worried about only buoyant forces when we submerged it. So when I talked you through what happens, which one's going to sink in the fluid, it was because we're going to submerge it in water, and water is so much denser than air, we can ignore there's probably some small effect in the air. In fact, we're going to measure that small effect right now. So, but the water dominated that problem. In this problem, there's no water, it's all about air. So we're going to take the air out from the outside of this and see if one of these guys sinks versus the other. But we can figure out which one it's going to be. So these two objects have the same mass, right? Because they're balanced right now on that balance. But which one's got a bigger volume? The hollow thing or the solid thing? The hollow one. So which one has a bigger buoyant force due to air? The hollow one. Because it's got a bigger volume, right? So if I take the air out from the outside, that big upward force due to the buoyant force on the big round guy, that goes away. And there's also a buoyant force acting on the solid piece over here, but it's smaller. So when I take them away, the relative change then is that there's much less upward force on the big guy and compared to that one. So which one's going to sink? I think the hollow thing is going to wind up sinking because we're going to remove a larger buoyant force and it won't be balanced anymore. So let's see if that's true. So I'll turn this thing on. So the air's coming out. Slow process. No one's going to get their head cut off at least. Except I might get in trouble if I break that. There it goes. Is it moving? Oh, I didn't have it open, sorry. So the thing is, it's an interesting psychology experiment. I have a scientist watching. I know what the answer's going to be. They will see it going, right? But it's not real. No, but that's real. You can really see it changing, right? Yeah, you see? It went down. So, and now I'll keep it closed. I'll do this in the right order this time, unlike I did last time. There's a little smoke up here. Anyway, that's because, so the thing I did wrong in the last demo is, I turned the pump off while it was still connected to the vacuum, and that sucks oil out of it. Not good. Good, you have to disengage it before you turn on the pump. Not that you care. So now take a look. See this thing that's really low? It's because it actually has more mass than the other one. How do we know? Because now there's an evacuated chamber. There's no buoyant forces at all. Because I took the air out. Forget water, I took the air out. There's nothing in there. So there's no buoyant forces in yet, it's heavier. But now if you give it a buoyant force by letting the air back in, right? And now this guy will get raised back up because he experienced a bigger buoyant force. Why? Because his volume is bigger. Right? The density of air is the same over here as it is over here. But the volume of the big object is larger. It hasn't quite made it. Oh, there it goes. Yeah, there it goes. Yeah, okay, good. You know, so I went to the South Pole one time, and I brought, and because I was doing an experiment down there, it was a lot of fun. And we went down and we brought pressure gauges with us. That we had them shipped, and then we took airplanes. I didn't take boats. And so then, when the pressure gauges came, all of us, at first we were tapping our gauges. The pressures, we were doing exactly that. Like, the pressure gauges were wrong. They said 540 torr instead of 760 torr. Torr is another word for millimeter of mercury. So instead of 760 millimeters of mercury, we had 540. But it turns out the pressure there is lower. It's like being up on a mountain. So it's because, in part because, there's two reasons why. The obvious reason is that it's very high up compared to sea level. But the second reason has to do with the rotary motion of the Earth. There's more atmosphere on the equator than, you know, for sort of obvious anyway. But beyond the scope of the class. The bottom line is that, yeah, if you go up to higher altitudes, as we discussed, the pressure goes down. And we were surprised how big of an effect it was. When you fly airplanes, same thing. They don't pressurize the cabin. They pressurize it as if you're at 7,000 to 8,000 feet. So the pressure's lower, and then you'll see all kinds of weird things happen. But anyway, very good. So good, that worked. And we were able to think it through. I could have calculated it all using Newton's second law and all the rest of it. You saw me get all mixed up a couple times in my signs and everything. So what I always want to do when I'm thinking of these problems is keep my head up and wits about me and just think it through logically. What's happening, right? There's only going to be three forces on either of these objects. There's a tension through the chain, there's a buoyant force, and there's gravity acting directly on that object, right? And so if I can keep my wits about me and say, well, I know they're balanced right now, and all three forces are non-zero. Then if I take away the buoyant force, what's going to happen? Buoyant force is bigger for bigger volume object. That answers the problem. So I know what the answer is going to be before I start, you know, putting the lead on the paper and try to solve the problem. That's how when I see an answer is wrong, I say I must have messed something up, and I figure out what my sign is. So it's good to have intuition about it. This is a tricky problem to think through, but we just talked it through. And I think, you know, that these things, fluids, the subject of fluids is vexing for a lot of students, but there's a few basic intuitions. If you have them, it'll help you think through almost any problem you'll see. Right? You'll be able to figure out, yeah, here's what's going to happen. Right? Buoyant forces only depend on volume. But let me ask you this sort of a puzzler, right? It's true that we're calculating. One way to calculate the buoyant force, right, is by thinking about the submerged volume and then multiplying it by rho of the fluid, because after all, this times this is just the mass of the displaced fluid times g, right? In other words, it's the weight of the displaced fluid, of the displaced water, or in this case, the displaced air. But does that mean that I can't float a battleship in a bathtub, right? So suppose I had a gigantic bathtub, much bigger than Archimedes, right? That would fit a battleship, and it fit exactly right. There'd be 1 inch of water, if it fits right in there, between the outer hull of the ship, this battleship, and the bathtub. Now, if I did that, if I got my hose and I got water around the outside and filled it up, right, there would not be enough water to actually equal this much volume, right? If I only give myself a centimeter or an inch or something. But would that work? Could I, in principle, and in fact, people have done this experiment, could I, and they do it all the time, could I float this battleship in a bathtub? Is that possible? So what do you think? Yes? No? Oh, no one voted. So like 5 people voted, and most people said no. So the answer is yes, you certainly can. The battleship doesn't care. Like, laws of physics are very local. So at the surface of the battleship, it's experiencing the pressure from the water. The battleship doesn't know how far away the bathtub is. In fact, if you blindfold me and put me in, and some of you are, I'm sure, fantasizing about blindfolding from me in the pool. If you were to do such a thing, right, I wouldn't be able to tell how far away the wall is based on how much pressure I'm experiencing on the side of my body. I might be able to tell based on the dynamics of the water. Like I push the water and I say, oh yeah, I feel, you know, whatever. Right, sure. But if I'm not moving, right? Yeah, because I got that kind of sense, you know. But if I'm in the water and I've got my eyes closed and I'm not moving, I wouldn't be able to tell based on the pressure how close the wall is. Just like over here, right? Doesn't matter what the shapes of these vessels are determined. They're all connected, right? They're all of the same height of the water. Why is that? The pressure is only a function of height. And so, in a similar way, the pressure inside that water doesn't care about how narrow the channel is between the side of the boat and the side of the bathtub, right? So in fact, you can float a battleship in a bathtub. And in fact, that's what happens when you have like these giant telescopes. So physicists and astronomers have these giant telescopes that are big. They're not battleships, but they're giant metal objects that are cylindrical, and they have them floating with oil around them inside another cylinder, and it works. It floats, even though the mass of the oil you put in is tiny compared to what the mass would be of the density of the oil times the submerged volume. The submerged volume is the whole volume of the telescope that's sitting inside this thing, right? So you don't actually need to have this much fluid in the problem, right, to make it work. It's just a calculational tool, right? It's just the way we calculate. It's the equivalent problem that if you were to take that telescope or the battleship, whatever, you put it in the center of the ocean, like in the middle of the ocean somewhere, or in the case of the telescope, it'd be an ocean of oil, right? But you submerge it in a huge body of fluid. Well, the amount of displaced fluid is just going to be the submerged volume, and then you multiply it by the fluid. That's how what the mass is, multiplied by g. That tells you what the buoyant force is, right? So it's just a calculational tool. Okay, great. So what we just talked through was how to relate heights and to pressures, and we thought through also how to calculate and think about the buoyant force acting on an object. And as I told you, it doesn't matter if the object's sitting on the bottom of the pool or if it's floating in the middle of the pool. It's going to always be there's always an upward buoyant force, right? And it's given by this formula. A lot of students, when I'm sitting on the bottom of the pool, they'll just say, there's no buoyant force, right? But there still is a buoyant force. And you might think, well, wait a minute. What if I'm standing on the bottom of the pool and there's no fluid between the bottom of my feet and the bottom of the pool? Now I've got fluid above me pushing down, but there's no fluid below pushing up. And I say baloney, because like this is a lot of pressure. Like as I showed you, there's a lot of pressure at one atmosphere. If you're in a pool, it's even greater. It's more pressure beyond that. So if you take your hands and push them together really hard and think, oh yeah, I squeezed all the water out between my hands. Well, probably not, right? There's still water molecules that insinuate themselves between your fingers, right? And the same thing is true underneath your feet. Now it's a little bit of a tricky problem if you have suction cups on the bottom of some object and you stick it to the bottom of the pool with a suction cup, or if you use a pump and remove all the fluid as we did here. Like okay, you know. So in some extreme cases, but if you have something sitting on the bottom of a pool, even if it's a very smooth, has a very smooth bottom face, you still calculate the buoyant force this way. You still can, and it still is the case that there's pressure of water underneath, even though you might take it first that there's no water underneath. So don't be fooled by that. There's one more thing to say about. Oh yeah, one more thing to think about too. So there are things that are lighter than air, like a helium balloon, right? If I have a helium balloon, right, and it wants to go up. In fact, I'm of two minds here. I have a daughter and she loves helium balloons, so I'll give them to her. But I've always railed against the fact that we sell helium to children and children's balloons. It's a mistake. In fact, there's a shortage of helium, right, as a result of our profit waste of helium. Helium is a ion out of the ground, and it actually escapes the atmosphere. It achieves terminal velocity very quickly at room temperature on the surface of the Earth. It's moving around so fast, and it's so light that it actually leaves the atmosphere, leaves the Earth. And once it's gone, it's very expensive and hard to generate more of the stuff. So we mine it the same way we mine oil, right? It's under the ground in Texas, and we have a lot of oil used to be. We're running out. But anyway, the bottom line is that so the reason I brought it up in this context wasn't geopolitical stuff, but you know, because it's a really resource. But if you have it in a balloon, well, why does a balloon float? The balloon floats for the same reason that we saw a change over here. There really is a change in the room, in the pressure between the bottom and the top of the balloon. So if you have a balloon tied to your wrist and it's doing this, and you're feeling a tug on it, some force, that force represents the change in the pressure of the air in the room from beneath the balloon to the top of the balloon. Which is bigger, the pressure just below the balloon or above the balloon? Below. Yeah. And if you're in a car and you tie, as it's happened to me, if you tie a balloon in the backseat of your car and it's doing this behind you and you're driving, right? And I make a left turn, which way does the balloon go? So yeah, so does it go into the turn or does it go out when I go through the turn? So it actually goes in. the air inside the car winds up getting accelerated. Well, so the air and the helium want to go straight. But if I turn left, right? So now we're doing, we can calculate the acceleration. It's v squared over r, right? And I'm going through some circle. Well, the air gets packed a little more on the right side. So it's kind of like there's, the pressure in the air in the car is greater on the right side than the left. So the balloon goes the other way, right? For the same reason the balloons go up, but everything else goes down. Helium balloons, I mean, go up, but everything else goes down in gravity. For the same reason, if you make a left turn in a car, everything else goes to the right, or my right. I'm sorry, right, left. Okay, fine. So I make a left turn, right? The massive things in the car go that way, but the balloons go that way because the air is because the buoyant it experiences something like a buoyant force, which is pointing the opposite direction. Anyway, so fun to think that through. Okay, so we talked really quick. I'll draw a picture of a barometer. We used to bring one out. I don't like to bring it out because it's a giant thing full of mercury and it's kind of nasty. So I'll just draw a picture of it. And it's really tall. Why is it tall? If you make a mercury barometer, so how do you make such a thing? You take an upside down test tube that's really tall. It's what it has to be like more than see, what is it, 760 millimeters? Yeah, 760 millimeters, almost a meter tall, right? And I should be really careful about what the bottom of this is. So I take this thing, it's over the bottom, it's closed on top, and there's a vacuum here, okay? And then I've got a fluid right here, right, of mercury, and it's inside of another tub down here, all right? Anyway, so the idea is I have an upside down test tube, it's really big, I submerge it underneath this pool of mercury, and I get a column that goes from the surface of this pool down here to the top of the column that's 760 millimeters of mercury. Why? Because this distance, so this is H, right? Rho G, sorry, that's weird, I did it again. Rho GH, where rho is of mercury, right, and H is this distance here. If that's 760, this equals 1 atmosphere. If H equals 760 millimeters of mercury. So if you wanted to measure the pressure in the room, how does that work? Well, we have this pool of mercury. The atmosphere is pushing down with a force, right, from the atmosphere. And the pressure up here is 1 atmosphere, right? This is gauge. Excuse me. This is absolute pressure we're talking about. So what's the pressure of a vacuum in absolute pressure? Come on, 0. In any unit, it's 0. Right? So that means in gauge pressure in atmospheres, what is the pressure of a vacuum? It's -1 atmosphere. That's a gauge pressure because you take the absolute pressure, 0, and subtract 1 atmosphere, minus 1 atmosphere. You got 1 minute left. So good. That height then is 760. That means, and you can just calculate with this formula. When the pressure goes up and down the atmosphere by subtle amounts, depending on the weather, right, and all these things, or they depend on each other. So the result is that if you want to measure this thing, you'd be looking at little tiny changes in the height. That's what the weatherman or weather person does to figure out what's going on. You have better ways of doing it than mercury barometers these days. But that's how a barometer works. The pressure in the atmosphere is pushing down here. Doesn't matter how deep this is. What matters is the difference between the height of this pool that's exposed to the 1 atmosphere. Right? There's 1 atmosphere here. There's 1 atmosphere just beneath the surface right here for the reason we talked about with that demo. And then we get up to here at 0 atmospheres, and so this height must be 760 millimeters if you work it out. So I guess what we'll get to next time then is I'll pick up with I'll talk about how hydraulic jack works. We'll talk about the continuity equation and dynamics, and we'll think about Bernoulli's equation in its full glory, and we'll give a review for the second midterm.